Good morning, learners. In this video, we are going to look at the Euclidean geometry questions from the Departmental November 2017 question paper. And we're going to, that's question 8, 9, 10, 11. It says give reasons for your statements. In question 8, 9, 10, 11, I just want to make it stop focusing quickly. And we're going to start with question 8. It says there, in the diagram, points A, B, D, C lie on a circle. A, B, D, C lie on a circle there. CE is parallel to AB, with E on AD produced. E lies on AD that's been produced, made longer. And then chords CB and AD intersects at F. Chord CB and AD intersects at F. D2 is 50. If D2 is 50 and this is chords in a cyclic quadrilateral angles in the same segment, that's also going to be 50. And then C1 is 15 degrees, so that there is 15 degrees. I'm just trying to calm down the camera. It's trying to focus. I'm just trying to get it to calm down a bit. Oh, stop it. I don't know why. Let me just quickly see if it helps if I lift it a bit. Okay, seems like that worked. There it goes again. Okay. Calculate with reasons the size of angle A. Alright. Now if that's 50, this is 50, and the alternate angles there, if I can get that angle in this parallel lines, if I can get that angle there, it's going to give me the value, which now I can do that quite easily because there's an exterior angle of this triangle. That's 15, so that's then 35, and then alternate angles is going to be 35. That's one method you can use. Or by angles in the same segment, this is 50, and then this is alternate angle, so that's 50, then this is 35, and then that's also 35. I think I'm still going to use exterior angle of the triangle is 50 there, then this is 15, and E is 35. So I'm going to start question 8.1.1 to say that angle E there is going to be 35. Angle E is 35 by exterior angle of the triangle CDE. The exterior angle is equal to the sum of the opposite interior, so 50 is 15 plus 35, E is 35, and then from there A is going to be 35 because it's alternate angles. In CE and AB parallel lines, CE and AB parallel lines, and then that's A. Then question 8.1.2 wants to know what is the value of C2. Now if that is 35 by angles in the same segment, C2 will also be 35 angles in same segment. And then 8.2, prove with a reason that CF is a tangent to the circle passing through points CD and E. So the circle passing through points CD and E, that circle there, I want to prove that CF is a tangent. CF, this one is a tangent. So basically, if I look at this as a circle, that's a tangent, then this is a chord of the circle, right? So the angle between a tangent and a chord, this angle must be equal to the angle formed on that chord. So angle E must be equal to C2, which, well, yes, it is. So that's not really difficult. angle E must be equal to C2. They are both 35 from 8.1.1. I already showed that there, and 8.1.2. So they are both 35. Then I can say that CF is a tangent to the circle through CD and E. And the reason that I'm using here is tan chord theorem. The angle between a tangent and a chord is equal to the angle on that chord. But I'm using the theorem backwards. This theorem says that, let me just sketch somewhere here. If I have a circle with a tangent, the angle between the tangent and the chord is equal to the angle formed on that chord. So this says if this is a tangent and that is a circle, these two will be equal. So now I said those two are equal, therefore this is a circle with that as a tangent. So I'm using it backwards. That means I'm going to use my reason as, there's no space there, so I'm just going to write it there, converse of tan chord theorem. Right, and that is question 8. Okay, that was not too rough on us. Let's quickly look at question 9 then. So, this looks a bit insane. Let's quickly look at this. Okay, it says, in the diagram, triangle ABC and triangle ACD, so these two triangles there are drawn. F and G are points. F and G are points on the sides AB and AC, respectively, such that AF is 3x, that's shown, FB is 2x, AG is 12y, and GC is 8y. Okay, that's all of that is shown there. HEK are points on the sides AD. HEK are points on the sides AD such that GH is parallel to CK, those two lines there, and GE is parallel to CD. So those two lines are parallel and those two lines are parallel. And now I must just keep my head not to get confused. Okay, prove that FG is parallel to BC. Prove that FG is parallel to BC. So I'm guessing the proportion theorem says that if these lines are parallel, these sides are in the same ratio. So I'm guessing I must show that the ratio is the same, and then by converse of the proportion theorem, these lines will be parallel. So let's start with that. Question 9.1.1. AF over FB, AF over FB is equal to 3x over 2x. 3x over 2x, and then if I cancel the x's, I have that is a ratio 3 to 2. Let's look at the other side separately because I don't have the information that this is the same ratio. I want to show that this is both the same ratio, 3 over 2, so that the proportions are the same, therefore the lines are parallel. So I want to work backwards here a little bit. So I have AG over GC. AG over GC is equal to 12y over 8y, and if I cancel the y's, I have 12 over 8 divided by 4 is 3, divided by 4 is 2. So both of this gives me a ratio 3 to 2, which then of course means that FG is going to be parallel to BC by converse of the proportion theorem. Converse of proportion theorem. The proportion theorem says if the lines are parallel, then the sides are in the same ratio. So what I did now is I showed that the sides are in the same ratio, then the lines will be parallel. So I'm using it backwards. Then I use converse of question 9.1.1. So let's look at question 9.1.2. I want to show that AH over HK, AH over HK, AH over HK is equal to AE over ED. AE over ED. You see, here is where I must now keep my head around me. Okay, let's quickly look at this triangle first, where AH and HK lies. So, in this triangle ACK here, do you see that side and that side is split by this and this? So, AH over HK, AH over HK will be equal to 12y over 8y, or 3 over 2, by the proportion theorem, looking at the parallel lines GH and CK. GH and CK, and then the other one that I want to show is AE and ED. Now AE and ED, also in this triangle ECD, AE and ED goes back to the same ratio. So AE over ED, AE over ED is also 12y over 8y, which is 3 over 2, still by the prop theorem. But now looking at the parallel lines, GE and CD, actually, GE and CD, and then, well, I've proven that AH over HK is equal to AE over ED. Okay, so that's what I wanted to do here. Then question 9.2 says, if it is further given that AH is 15, so AH is 15 and ED is 12, ED is 12, calculate the length of EK. EK. Okay, yoi. Okay, ED is 12. I'm going to have to look at this here. It's given that AH is 15. Okay, so if I use this, AH is 15 over HK is equal to, and AE, I don't know, and ED is 12, right? So they gave me that AH is 15 and ED is 12. I want to calculate the length of EK. EK is ED minus KD, or HK minus HE. I'm going to have to work with that somehow. HK, there, HK. I want to work out the length of EK. So EK is HK minus HE. ED is 12. Okay, so ED is 12. IH is 15. I think I must just work out something else here. HK. And IE is also part of that. IE is 15 plus HE. IE is 15 plus HE. And HK there is EK plus HE. Is HE plus EK. Okay. Alright. So I want to work out the length of EK, right? Which that's fine if that's a missing variable there. But then I wrote now the other two both in terms of HE. So I can clearly see I must try and get the length of HE here. Or maybe try and get the value of Y. Okay, let me quickly work out the length of HK, because I know AH to HK, AH to HK is 3 over 2, right? So, right, I know that AH over HK is a ratio 3 over 2, and it's given to me that AH is 15, right? HK. So if I use this, I have 30 is equal to 3HK. So I have that HK is 10 units, okay? So HK is 10 units. I'm trying to get the length of EK. HK there, this is 10 units in total. So AE over 12, AE over 12 is equal to 3 over 2, which I know already. Then AE to AE is equal to 3 times 12 is 36, which means AE is 18. Okay, so let's look at the sketch. AE is 18, then HK is 3, but HK is 10. Now, IE there. IE is 18, so that HE is 3, right? And then HK I calculated as 10, that means EK is 7. Okay, EK is 7. So EK is 7 units. Okay, I need to really look at the sketch here. Okay, so what I first started to do, this didn't really help me a lot because I have too much missing information. Then the second thing I started to do is I started working with this year, because they gave me the length of ED and they gave me the length of AH. So since I know that AH over HK is 3 over 2, and I have now AH is 15, I can use that to work out the length of HK, that one. Okay, and then since I know that AE over ED is 3 over 2, and they gave to me the length of ED as 12, so then that means I can work out the length of AE is 18. And now if I have AE is 18 and HK is 10, I need to look at the sketch. You see HK is 10 and AE is 18, where that's given as 15, so that's 3. Then I have that's 10, and this is 3, and then obviously 7 to make the 10. So EK is going to be 7 units. Okay, that's question 9. Let's look at question 10. I don't actually work through the questions before I start recording the video, because I also want you to sort of see the thought processes that I go through to solve the problems. And if I already worked them through, then I know what to do, and then you don't see how I got there. So I try and just do the videos to unprepared, to help you see how to approach the questions, and I hope that helps you. In the diagram, W is a point on the circle with center O. V is a point on OW. So V is a point on OW there. Chord MN is drawn such that MV is equal to VN. The tangent, I see the line from center to midpoint of chord is perpendicular to the chord, that theorem there. So I'm going to mark that there. Chord MN is drawn. The tangent at W, so this is a tangent as well, meaning what? That angle will be equal to, well, that's not going to help me. Okay, but that's a tangent is perpendicular to a radius, so I can also mark that in there. A tangent is perpendicular to a radius. The tangent meets OM produced at T and ON produced at S. Give a reason why OV is perpendicular to MN. OV is perpendicular to MN. Question 10.1. 10.1, why is OV perpendicular? That's because the line from center of circle to midpoint of chord is perpendicular. 10.2.1, prove that MN is parallel to TS. Now I can use the corresponding angles equal there. I must just state that that's also 90. So angle OWS is also 90 degrees because the tangent is perpendicular to a radius. And then I can say that MN is parallel to TS because I have the 90 and the 90 perpendicular. So the converse of corresponding angles. I feel like I've explained converse now quite a few times, but I'm just going to mention again because I know it's a term that some learners struggle with. The theorem states that if the lines are parallel, then the corresponding angles will be equal. So what I did in this question is I showed that the corresponding angles are equal, therefore the lines will be parallel. So I'm going backwards, then I'm using converse of as my reason. And then 10.2.2, prove that TMNS is a cyclic quadrilateral. TMNS is a cyclic quadrilateral. So to have a cyclic quad, I can either show maybe that the exterior angle is equal to the opposite interior. So I must show that N1 is equal to T or M1 is equal to S somehow. Or alternatively, I must show that the opposite angles are supplementary. So this one plus that one gives me 180 for some reason. Or you can show angles in the same segment, but there's no diagonal lines drawn in here. So I don't have the angles in the same segment. But those are the three methods you can use to show that cyclic, a quadrilateral is cyclic. Oh, I wish this thing would stop flickering like that. The camera focuses itself and then it thinks it's not focused and then it's trying to focus and okay. So I'm trying to show that this angle there is equal to that one. Now this angle here will be equal to that one there. N1 will be equal to M1 because this is an isosceles triangle having two radii there, and then since I showed these two lines are parallel, can you see that one will be equal to that one, and then these two are equal, thus I have a cyclic quad there. So that's what I can do. I'm sure there's really more than one way. If there's any learners in the audience watching this video now that did something else and you think that's also a valid way, please share them with us. So I have here N1 is equal to M1 because the radii are equal, and then I have angles opposite equal sides there. The angles opposite the equal sides, which are radii, that's equal. Why they are equal? It's because they are radii, so I must just state both. So N1 is equal to M1, and then M1 is equal to angle T. Those are corresponding angles in the parallel lines MN and TS, which I've shown parallel in the previous question. So N1 is equal to T. You can see that clearly there. N1 is equal to T, and that means then that TMNS is a cyclic quad. My reason for that, yet again, converse of exterior angle of cyclic quad. Why I use converse of, again, I'm just going to mention it. If it's a cyclic quad, the exterior angles or the exterior angle is equal to the opposite interior. This is not a cyclic quad, but since I've shown that this exterior angle is equal to that, the exterior angle is equal, then thus it will be a cyclic quad. So I'm using that theorem but backwards. Okay, so converse. 10.2.2, then I'm looking at 10.2.3, which says that show that OS times MN, OS times MN is equal to 2ON times WS. Wow, 2ON times WS. Okay, now this has to do something like this, always comes from something like this that's been cross multiplied, right? And since there's a 2 there, I'm guessing also they substituted something with something else. I'll check now, but this comes from similarity or proportion theorem. So I'm just going to look at OSMN. Where are they? I have OSMN, that one. And ON, 2ON, but ON, and WS. Okay, so it might be that this side and this side, you see, forms a triangle there, that I'm working with this triangle. And then this side and this side forms a triangle. But now the 2 also makes me think somewhere I must work with a double, which makes me think instead of working with WS, I might work with this, which WS is then, or 2WS is TS, and that's where the 2WS might come in. So I'm going to just start off by working with this triangle that has the ON and the MN, the ON and the MN in it, and then the big triangle that has the OS and the ST. Since this is a cyclic quadrilateral, I'm just trying to think of a valid reason why those two lines might actually be equal. But I'm guessing if you work with this is well, this triangle there is in the same ratio as that triangle, is similar to that triangle. This one is similar to that one. This one is similar to that one. So the ratio of this to this is going to be the same as the ratio of this to this. And since those are equal, then those will also be equal. Right. I'm going to do similarity proof first with this triangle and that triangle. This one will be double that one. Okay. So, I have here that in this, I'm going to use this triangle on the left-hand side. I apologize for the noise outside. My neighbor is cutting the grass, and this triangle on the left hand side and this triangle on the right hand side. When I do a similarity proof, I always try to list one triangle on this side and the other one on that side, so that my listing here is easier. So I'm going to say the small triangle on the left hand side has angle M1, angle O1 and 2, and angle N1. You see this is all angles M1, O1 and 2, and N1 is all angles from my smaller triangle on the left hand side together. And then my big triangle, the T, the O1 and 2, and the S lies in the big triangle, which I'm also going to list all on this side. So can you see M1 is equal to T because they're corresponding angles. M1 is equal to T, their corresponding angles. MN parallel to TS, and O1 and 2 is equal to O1 and 2. It's the same angle, or I call that a common angle. And then N1, well, I can also say is equal to S because of corresponding angles. But if two sets of angles are equal, the third one by default will be equal. So you can also just say third angle of the triangles. And then the listing here is a little bit easier. So I see that MON, triangle MON is similar to triangle TOS. I just follow the angles, angle MON. If this was now PNT, so for instance, I will list the N there. By angle, there's my similarity, and then from similarity, I can write down that MO over TO, MO over TO is equal to ON over OS. ON over OS is equal to MN over TS. MN over TS from similarity. And then I'm trying to show here something with OS, MN. So there's MN, OS, ON, and WS. ON and well, TS is 2WS. So I'm going to work with these ones because the MO and the TO is not present there in the question that I'm currently attempting. So from there I can cross multiply ON times TS is equal to OS times MN. So I have OS times MN is ON times TS, and I want to replace the TS with 2WS. OS MN. So 2 ON WS is equal to OS times MN. So that's the proof. But before we conclude this, you must actually just have some valid reason why WS will be exactly half of the TS, because it's not necessarily given that those two lines are equal. It's given those two lines are equal, but that's not necessarily equal. So one thing you can maybe just mention that triangle OWS will be similar to triangle OTW, because that angle is equal to that angle is equal to that angle. That angle, I already said just now, those two are equal, and those two are equal because the corresponding angles. So that's something you can do, or you can maybe mention that this line OW, since that's a radii and a radii, and those are given equal, these two triangles are exactly OMV. Let's quickly mention that here, just to have some sort of argument, is that triangle OMV is going to be congruent to triangle OMV. ONV is going to be congruent to ONV by side. You can see radii side, that's given, and that's a common side. So it's going to be congruent, which means that OW is a line of symmetry there, right? And since that is a line of symmetry in this triangle, and this just extended is also going to be a line of symmetry of that triangle. So TW and WS, which means TW and WS is equal. So just have some sort of argument there why you replace that TS with 2WS when you do this question. Okay, then that's question 10. Question 11. In the diagram, chords K, M, M, N, and K, N are drawn on the circle with a center at O. P, N, Q is a tangent to the circle at N. At point N, prove the theorem that M, N, Q, this angle there, is equal to angle K, tan chord theorem. Right, now to prove tan chord theorem, you have a construction. You should actually use a ruler. I don't think I have a ruler close by here, so what I'm going to do is just use my free hand, but please you use a ruler. So from the point of tangency through the center of the circle, right through to the other side, you want to draw a diameter there, and then depending on the sketch, you're going to connect this diameter either to M or to K. Connect it to the one you want to prove equal here. So since I want to prove MNQ, this angle here is equal to that angle, I'm going to connect my diameter to K. If the question was to prove this equal to that, I would have connected it to the other side. Just label that something. You can choose any letter that's not on the sketch. A is perfectly fine. And just to make my life easier, I'm going to label that 1 and 2. 1 and 2. Just on a side note, don't do this construction on your question paper and then answer in your answer sheet. The person marking your work does not have your question paper with you. Most of the time, the sketch will be in your answer booklet. Draw this on your answer booklet, not in your question paper. All right. If there's no sketch in your answer booklet and you want to do the construction, either write what you constructed there in your answer or redraw the sketch and then you can add stuff to the sketch. All right, so this is my construction. Now I'm still going to do the proof on here. This proof works like this. So AN is a diameter. I drew it that way. So then K1 and 2 together will be 90 degrees because it's an angle in semicircle. Semicircle. Okay. Angle in semicircle, and then N1 and 2 together will also be equal to 90 degrees because a tangent and a diameter is always perpendicular to one another. Tangent is perpendicular to diameter right now, but N1, look at this, N1 and K1 is equal because they're angles in the same segment, you see. So the N1 and the K1 is equal, N1 is equal to K1. So now I have here currently, that's angles in the same segment. So now I have here currently K2, which is equal to 90 minus K1 from there. If I just take the K1 over, K2 is 90 minus K1. And in the same way, N2 is 90 minus N1, but the K1 and the N1 is the same thing. So N2 and K2 is both 90 minus the same thing, which I've shown then. Therefore, K2 is equal to N2, and K2 is the angle K and the N2 is MNQ, which they wanted me to prove equal. So there is my proof. Question 11.2. This is one of the examinable proofs. I mean, you must know these ones anyways. But yeah, it's sometimes just good to see them again quickly. So okay, question 11.2. In the diagram, BC is the diameter of a circle. The tangent at point D, there's a tangent. Now, if that's x, then this is going to be x because the angle between a tangent and a chord is equal to the angle formed on that chord. So the tangent at point D on the circle meets CB produced at A. CD is produced to E such that EA is perpendicular to AC. BD is drawn. There we go. Let C1 be X. So C is X. There's an X. Great. Give a reason why D3 is 90 degrees. They said here that BC is a diameter, so that's 90 degrees. D3. Okay, question 11.2.1a. D3 is 90 degrees because it's an angle in a semicircle. Right. Number B. Give a reason why ABDE is a cyclic quadrilateral. ABDE because the exterior angle is then equal to the opposite interior. So converse of exterior angle of cyclic quad. And number C is give a reason why D2 is X because of tan chord theorem. Tan chord theorem. And then 11.2.2, 11.2.2, prove that AD is equal to AE. AD is equal to AE. So what I in essence want to prove is that this two angles there is equal. Now this is an exterior angle of that triangle. I don't have that there, but let's quickly see. D1, that's 90. So D1 is 180 minus 90 minus X. Let's write that down. So D1, because the angle is on a straight line, you see D1 plus X plus D3, which is 90, is going to be 180 angles on a straight line. So D1 is 180 minus X minus 90 angles on a straight line is supplementary. So D1 is going to be 180 minus 90 is 90 minus X. And E, sum of angles in a triangle, is E plus 90 plus X. So E is 180 minus 90 minus X as well. So E is 180 minus 90 minus X, sum of angles in a triangle, sum of angles in a triangle, and also 180 minus 90 is 90 minus X. So there I have it, that D1 is equal to E, and if those two angles are equal, then those two sides will be equal, AE and AD, because they are angles opposite equal sides then. So AD will be equal to AE because they are sides that lies opposite equal angles. Let me just also quickly mention this. In isosceles triangles, if it's given that those two sides are equal and I want to say these two angles are equal, I say for instance ABC. So if this is the scenario on the sketch, those two are equal. So I say angle, my statement here is angle B is equal to angle C. My reason will be they are angles. If I say angle B is equal to angle C, those are angles that lies opposite equal sides on the sketch there. And if it's somehow on the sketch given, or I've proved now that the angles are equal, what I've done here is the angles are equal, then from that I conclude the sides are equal. So now I say AB is equal to AC, or whatever the case might be. Those are sides, you see, sides that lies opposite equal angles. So just take note of the two reasons when working with isosceles triangles. 11.2.2a, and then we look at 11.2.2b. Prove that ADB is similar to ACD. ADB, that one there, ADB is similar to ACD. ACD. Okay, in question, in triangle, I'm going to, in triangle, ADB and triangle ACD. ADB, ACD, that angle A2 lies in both. So I can say angle A2 is equal to angle A2. It's common angle. It's the same thing. So then I'm looking for D to be equal to C. The angle D2 in this triangle, D2, is equal to the angle C in this triangle, angle C. Because I already stated that D2 is X there in question 1.2.1c, so I have the information that they were both X. And then in this triangle ADB, on the left hand side, I have A2, I have D2, I need B2 still. So B2 is equal to, and then in the triangle ACD, I have A2, I have C, I need the D, which is D2 and 3. D2 and 3. Both of those is 90 plus X, 90 plus X, but I don't really need to prove anything because I have 2 equal already. The third angle of the triangle will by default be equal because the sum of the angle in two triangles are 180. So this plus this plus this and this plus this plus this must be 180. But those two are the same already. So if I have, for instance, 120, then this is also 120. Then that must both be 60, obviously. So the third angles will be equal by default, sum of angles in a triangle. And then I can say that triangle ADB is similar to triangle ACD. ACD by angle, angle, angle. And that's my proof. Okay, it is further given that BC is 2AB, which is 2R. BC, that length there, is 2AB. So that AB is R and BC is 2AB, which is 2R. Okay, so I have there a ratio R and 2R. And then obviously that's going to be 3R, can you see? So BC is 2R and it's 2AB, which is then obviously R. Prove that ID squared is 3R squared. ID squared. So now I'm working with this similar triangles there. So I'm going to work there. Question 11.2.3a. From the similarity there, I have that AD over AC is equal to DB over CD, DB over CD is equal to AB over AD, AB over AD from similarity. And let's quickly, I just first write down my similarity and then I check what I need. I need AD squared. So I'm guessing I'm going to work with this one that has the AD and this one that has the AD. And since AC, I can see on the sketch AC is going to be 3R and AB is going to be R. So I can work with that. AD is equal to AC, which is 3R, is equal to AB, which is then R over AD. I just substituted the R, so I don't really need the reason. So AD times AD is going to be 3R times R, 3R squared, which is what I wanted to prove. Easy enough. Okay, right. So in the previous video, I started with question 11.2.3 from the November 2017 question, and I struggled a bit with number 11.2.3b. So I stopped the video and I just went and looked at the sketch first, but the sketch is now scratched quite a lot, so I just redrew the sketch here. So far we have that AB is R and BC is 2R. Okay, and then in the question A we showed that AD squared is equal to 3r squared. So that means, and this is the first mistake I made, is that AD is root 3r. So that's root 3r. And since earlier we also showed that these are equal, that's both root 3r. And that's 90 minus x each. So I want to show that this is an equilateral triangle. So I also want to show that that's 90 minus x, or alternatively I want to show this is 60, 60, 60. And since this is a 90-degree triangle, I can use my normal trigonometry that tan of this angle will be opposite 3r over adjacent root 3r. So I can use that tan of 90 minus x is equal to 3r over root 3r. The r's cancel and I have 3 over root 3. Let's just maybe rationalize the denominator there. So I have 3 root 3 over 3, and then the 3's cancel, so root 3. So tan of 90 minus x is root 3. And you can use your calculator, shift tan root 3. So I'm going to do shift tan root 3 gives me 60. So 90 minus x, that angle there is indeed in 60 degrees, one of the special angles also. So 60 degrees, 90 minus x is 60, which means angle E is 60, angle D1 is 60, because it's also 90 minus x, and that means by default that angle A1 will also be 60 by sum of angles in a triangle. Sum of angles in a triangle, and then since I have 3 60 60 60 angles, then the side lengths are all the same, so it's an equilateral.